So let's get back to the sine wave formula, expressions for phase shifted sine waves. So with this with formula, we can calculate things like the amplitude of a signal, a phase shifted signal, because we can take the difference or the sum of the waveforms and calculate the magnitude, in this case the value y. So when a sine wave is shifted to the right of the reference, remember we called that lagging, by a certain angle, there's our other Greek letter phi, where the reference is the vertical axis, the expression then becomes y is equal to the amplitude times the sine of the difference, theta and phi, where y represents the instantaneous voltage or current and A represents the amplitude or the peak value for the expression. When a sine wave then is shifted to the left of the reference, remember, leading by a certain amount, phi, then the general expression becomes the sum of the two angles we take the sine of. So y is equal to the amplitude times the sine of the sum of angles phi and theta. So we can see then in the diagrams below how that shifted sine waves, whether it's lagging or leading by angle phi, fits into the expression of y sine of the angle. So if we look over here to the right, determine the instantaneous value at the 90-degree reference point on the horizontal axis for each of the voltage sine waves. So you can see here we've got A, B, and C. Each of them have a different amplitude. Each of them have a different phase shift. So A is crossing as we normally would see it, starting at the origin and crossing at 180 and 360. B has been moved to the right, to the left, sorry. B has been moved to the left by 20 degrees. C has been moved to the right by 45 degrees. So, although we have different amplitudes here, you can see that we can treat each one of them by the phase shift. So, the sine wave A is the reference. The sine wave B is shifted to the left by 20 degrees with respect to A, so it leads. The sine wave C is shifted to the right by 45 degrees, so with respect to A, so it lags. So let's start to put this together. So the voltage for sine wave A is V peak times the sine of theta. Okay, so the 10 volts we can see is the max amplitude, and we take the sine at 90 degrees is where we're going to find our maximum, is equal to 10 volts. Okay, here's another one of those sine values. The sine of 90 degrees is always 1. Write that down in your notebook. Now V sub B, the voltage, instantaneous voltage B, is equal to V peak, the sine of theta, plus the angle phi for sine wave B. So if we look at B, we can see that B's max is 5 volts. So 5 volts times the sine of 90 for A plus 20 degrees gives us 5 volts times the sine of 110 degrees, or 0.9397 times 5, 4.70 volts then becomes the amplitude for the sum of those two. Now the difference between A and C, between angle theta and phi C, then is 90 minus 45 degrees, because 45 degrees, you can see here, is the phase difference for C behind A. So we have a difference of 90 minus 45. 8 volts is the maximum for C. sine of 45 degrees, again, that's another one of those magic values. The sine of 45 degrees is always 0.707. This one is going to become very important in your studies, so make sure you recognize that one, sine 45.707. Anyway, so it's telling us that basically 70% of 80 of 8 volts gives us 5.66 volts. So that's how we deal with phase shifts and sine waves in calculating the amplitude. For the next section then, we're going to introduce phasors. How do we use these relationships now so that we understand something called the magnitude and the direction, or the phase angle? So phasors are going to provide a graphic means for representing quantities that have both magnitude and direction, or angular position. Okay, phasors are essentially and especially useful for representing sine waves in terms of their magnitude and the phase angle, and also for the analysis of reactive circuits discussed in later circuits. So if you had, again, ET111, you've been introduced to this. If you look at my videos, go back and look at my videos for the 111 course, you will see that was introduced in ET111. So after completing this section, we'll be able to use a phasor to represent a sine wave. We'll define the phasor, explain how the phasors are related to the sine wave formula, draw a phasor diagram, and discuss the angular velocity. Okay, so this is going to prepare us for our studies as our circuits become more complex by using resistors, capacitors, and inductors. So get a firm grasp on this, because you're going to need it for the rest of the course. In electronics, a phasor is a type of vector, but the term generally refers to quantities that vary with time, such as what we're looking at now, sine waves. Examples of phasors are shown below in the diagram 1128. The length of the phasor arrow then represents the magnitude of the quantity. So this tells you you can pull out a piece of graph paper and plot these things on a graph paper by understanding that the length of the vector, or the arrow that you draw, has a direct relationship of the magnitude. The angle theta relative to the 0-degree mark represents the angular position, as shown in part A, for a positive angle. Okay. The specific phasor example in part B has a magnitude of 2, so we can see that down here, and a phase angle at 45 degrees, perfectly dissects between 0 and 90. The phasor in part C has a magnitude of 3. Notice it's fully on the axis, pointing in the negative direction, and a phase angle of 180 degrees. This is going to be important because that 180 degrees, when we take the angle, is going to give us a negative value. The phasor in part D has a magnitude of 1 and a phase angle of minus 45 degrees, or 315 degrees positive if we go all the way around counterclockwise. Notice that positive angles are measured counterclockwise, or CCW from the reference, and negative angles are measured clockwise from the reference. So this is getting us set up to understand what a phasor is, and what it looks like on graph paper, what it looks like in the phasor diagram, and how we handle the magnitude and the direction, or the angle. So when we come back, we're going to take a look at phasor representation of a sine wave.